We can start, ma'am.
All right. Do you see my screen?
Yes, ma'am.
And do you see my face?
Yes, ma'am.
And are we online already, like the YouTube?
Yes, ma'am.
Okay. Thank you so much for confirming. Good morning, everyone, and I welcome you for our last talk of the series of Futuristic Fridays that CCMB has been doing with CSIR HRDG in Delhi. In Futuristic Fridays, we have had speakers who are experts who work with AI and big data in health and biology. And today we have Dr. Anshu Bharadwaj joining us from CSIR in Tech Chandigarh. And in her talk, she will be talking about how she uses AI and machine learning models in drug discovery, in finding new drugs for different diseases that we all want to fight and eradicate. But before I hand over the mic to Anshu, I will want to quickly tell our audience today, who are both present in person at IMTech and probably other labs as well as on YouTube, that this series has had 4 speakers, and only when one registers by clicking on this participate now button, you get to see also a set of quiz for each talk by each expert. You have to participate in those quizzes, and based on your performance in those quizzes, we will be selecting about 20 to 25 students for a short hands-on training by Dr. Anshu Bharadwaj and Dr. Arvind Rao in the months of May and June. So Dr. Bharadwaj's session will be in May and Dr. Rao's session will be in June. And we will really be looking forward to meeting some of the very, very smart and invested young people who want to not only hear these speakers speak, but also want to learn these tools and play with these tools hands-on themselves. So do participate in those quizzes, and we will be looking forward to selecting some of you for these sessions. And I will also want to take the opportunity to tell you a little more about what Jigyasa does. So if I go to the Jigyasa platform, Jigyasa is a program where CSR labs connect scientists with students and educators. And we really believe in doing this so that our classrooms become more scientifically better equipped, and we are together able to improve the scientific temperament of our young people. We also create a lot of content in various different formats that ranges from games to comics to simulations to videos, podcasts, you name it, and we have it. And the idea is that educators take advantage of these content and use them in their classroom actively. And young people who have access to internet themselves through laptops or phones, you are also you will probably find many of these very interesting for usage at your own personal level as well. So go ahead, explore the content that we make. Teachers take advantage of the different programs that we run, which are also, many of them are in-person sessions in labs, and let's make our science learning more fun and engaging. With that, Anshu, the mic is over to you, and you can start the talk.
Thank you, Dr. Somdesan. Yeah. Am I audible?
Yes, Anshu, you are.
And can you see me?
Not yet.
Okay, just a second.
Anshu, I will also request you to, before you get into the crux of your talk, if you can spend a couple of minutes explaining your career trajectory to the students.
Just 1 second, Somdita.
Yeah, sure. Great, I see you now.
Yes. All right. So I hope I'm audible to everyone.
Yeah.
All right, good. So what I'll do is Before I start and share my presentation with all of you, as Somdata said, a brief about me. So I come from a small town called Gwalior, right? And since my childhood, I was very much interested to basically see what I can do to alleviate, the health issues that I see around myself. A lot of my family members were sick, and I was saying they were undergoing surgeries, and the process was very painful. And I was also always asking, why is not there a simpler method? What I can do to make it better. And that is the motivation behind me to take up research as a career to see how I can help society in living a healthier life. Now, how do you do that? You can either become a doctor, or you can actually do research to see how you can find new solutions. So while I was finishing my master's project, I saw the launch of the human genome. And that was almost 23 years ago. Okay. And that 23 years ago, when I looked at what is the data that the human genome generated, as in for the first time, we were able to read the blueprint of life, which was our DNA. And it was a huge excitement globally in every researcher, everybody was thinking, since now we can read our DNA, we should be able to understand why disease happens, and we should also be able to understand how to solve it, right? And that basically made me excited to see now how do you read that DNA, because even the first draft was 3 billion bases. So you can imagine how many zeros after 3. There is no manual way to read such big amount of data, right? And that is what prompted me to learn computer programming. So I'm a biologist by training, but me and my team do computer programming and data analysis on a daily basis. So what computer scientists do, we do, because till the time you understand biology and you also understand computer science, you will not be able to address very intense problems in biology. And the entire series, as Dr. Somdata has told you about Futuristic Fridays, is the fact that how different methods in computer science, in data science, is helping people to address problems in biological sciences domain. All right. So with that brief introduction, let's get started. Right. So I hope, Somnata, my slides are visible.
Yes, Anshu. It's also in full screen.
Right. So great. So basically, let's get started. So we are today discussing machine learning in the area of drug discovery. All right. So let's understand how we started doing drug discovery many years ago. Okay. Let's go in the past to understand what we are doing today. So very long ago, doctors used to pour drugs of which they know little to cure diseases of which they know less into human beings of whom they know nothing. And I'm talking about, you can imagine the dates, right? I'm talking about a very old time when everything was pretty much hit and try. Because when you eat food, there is an impact of food in your body, right? So we very early on started to understand that whatever we eat actually has an impact on us. So now what we are eating can also treat us. And this is, this was traditional knowledge that what got generated over years. But slowly we realized that it was a lot of hit and trial because it is not really something that even targeted treatment was not happening. And many years we started to learn what really works, what really has not worked. And then what happened a couple of years ago, as in say 60 to 70 years ago, scientists discovered a new drug which is called as thalidomide, right? It was made by a German pharmaceutical company and was sold in across 50 countries, you can see, from 57 to 1961. And what was the effect of that drug? So pregnant women who feel morning sickness used to take this treatment. And they used to feel good after this. So obviously the drug worked and everybody was happy. But subsequently, what people started to report is this. The children born to these pregnant women actually were born with very small legs and hands. And this condition is called as phocomelia. So at that time, people realized that it is not only the immediate effect of the drug, but one has to actually think about the long-term effect of the drugs, right? And this basically then led to something which is called as a rational drug design approach. where you then test, try on everything. But since the entire problem is still traditional in nature, which is trial and error, when you start to do drug discovery in a lab, it takes around 10 to 15 years. Okay. However, with predictive AI machine learning models, one can expect that the drug discovery can move faster. It will become simpler. Okay. How? Where is AI helping? How will it help to make drug discovery faster and simpler? Let us try and understand that today. But for that, we first have to understand what drug discovery means. So we all know why we take medicines. Why do we take medicines? When do you take a medicine? To cure sickness, right? Which means there is a chemical compound that you eat and it makes you feel all right. Okay. So when a drug discovery process happens, drugs are not discovered randomly, as in it's not something that, that you can just say, okay, this is a drug, because then you go to a pharmaceutical, you actually go to a pharmacy, say, I want X drug. That person has the drug. From where is it coming? Somebody is manufacturing it. Who is manufacturing it? The person who discovered it. There is a huge pipeline that gets involved. So let's understand what the drug discovery process is and why artificial intelligence and machine learning are actually used. Now we know it's not one disease condition that we deal with. There are so many disease conditions, right? So in the first step, one needs to identify what disease are we planning to cure. And how do you identify a disease condition? First is, if there are too many people dying of a disease condition, you need a treatment, right? That's the first condition. Second is, there is no treatment available. Or third, treatment is there, but it doesn't work. Like say, for example, if you look at today, cancer treatment does exist. But is it working completely? It is not. So many people still die of cancer. The treatment is out there, but it is not really working. So what do? You select one of the disease conditions to actually start your drug discovery process. Say, for example, in this case, we are starting with disease B. Okay. Then you find the cause of that disease. Is that disease happening because of changes in our DNA, which is genetic in nature? Or is that disease happening because we are exposed to infections? Because for both the conditions, the approach for drug discovery will be different. Now assume that the disease that we are trying to cure is an infection. Like say, for example, your COVID infection, other bacterial infections, okay? Then you have established that the disease is not happening because of you or your genetic makeup. The disease is happening because of an infectious agent attacking you from outside. Okay. And then you identify what agent is it, what type of bacteria it is. You need to know what is impacting you, isn't it? And then once you have identified the cause of infection, then you find what is the weakness in that organism that you can target. So if you hit somebody on a weak spot, what will happen? What will happen when you hit somebody on a weak spot? Okay, let's reframe the question. If you want to really kill a human being and you have a bullet, where do you hit it? Head or heart. If you hit it in the hand, the person may not die, right? So how do you now identify the head or heart of a bacterial system that you don't even see? So that's the next challenge. That how do you identify those points where you can target? And then you look for how to target it with. So you are actually looking for a drug. How many possible drugs can be there? They can be 10 to the power 60. It looks like a very big number, right? You can say billion, trillion, but it is beyond that. Which means that there is no manual way of looking at this data. So you use computer. So you use the power of computers to say, okay, can I shortlist or select one from this repository and then test it in lab, see if it works in mice, and then test it in a human. If when you do human testing, which is called clinical trials, and disease B goes away, it tells you what? That your drug has worked because you have actually got the expected effect. The person is cured of the disease. There is no more infection now, right? Now, at each of these stages in a drug discovery process, starting from here to here, At every step, artificial intelligence and machine learning can be applied. Okay, all stages. But today, for sake of discussion, I have picked up this stage for you to say how do we actually identify compounds from such a big repository, from such a big chemical space. How do you now identify compounds that might work as a drug for a disease condition by using machine learning methods? Okay, so far so good? Okay. Now, when you use the word learning, so what it entails? The machine is learning from something. From where is it learning? How will it know what will work as a drug? Which means there is some data that is previously generated, which is helping the machine to understand which chemical compounds can work as a drug, which chemical compounds may not work as a drug, isn't it? And that is where we started to understand this. So carbatamide is an anti-diabetic drug. It actually is one of the first anti-diabetic drugs, but it has bone marrow toxicity. So over a period of time, a lot of people then started developing other drugs because it was causing toxicity. So they came up with another drug which is called as tolbutamide. If you look at the structure of both these drugs, what do you see? If you look at the structure of both these drugs on the screen, what do you see? Is there a difference? Where is the difference? Are they different? First of all, yes, no. Yes, very good. And where are they different? Exactly. Now imagine just a small functional group is the only difference in between these two structures, converting a drug from unsafe, toxic to a safe drug. So you can imagine how a small chemical change actually changes the property of drug molecules. And this concept is called as structure-activity relationship. So the structure of a compound actually changes its activity. And this is what one can learn from. Because now you can look at proteins like this small molecule structures and say what changes you make so that it becomes drug-like. Okay. Now over years, a lot of people, actually a lot of pharmaceutical industry, academic setups have been doing drug discovery. So over years, people identified that any of these entities, if they are in your drug molecule, they make the drug molecule toxic. So now you know this has to be avoided. Because a potential chemical has these entities, it is going to have a problem. And they might not be able to drug. So over years, when we started learning this repository became very, very big. So the drug discovery and development process, which was pretty much a medicinal chemist or a pharmacist looking at, or a pharmacology expert looking at data in a very manual manner and trying to say, okay, let's try this, let's change this functional group, let's make these modification. Now imagine doing that with 10 to the power 60 possible space. Can you do that? You can imagine what 10 to the power 60 is, how many zeros after 10? Now, can you manually even draw so many molecules? You cannot. But you now have to try what works in this intense drug discovery pipeline. And this is where machine learning actually allows us to make use of the technology we have to identify drugs with the desired properties, like designer drugs. And how does it do that? So tell me, how many of you have used at any point some maps to navigate streets? When you start from home to go to some place, how many of you actually open your phone and say, okay, and how much time I'll reach from X to Y? Raise your hands. A lot of people, right? And for the kids here, your parents have seen your parents looking at your mobile phone saying, okay, let's start now. It's going to take 30 minutes. The Google map is saying it's going to take 30 minutes, right? How does Google know? How much time will you take to go from one place to another? If you look here, it is actually telling you 3 routes to go from one place to another place, right? At one, it is showing 3 hours, 35 minutes, 4 hours and 5 hours. From where Google is getting these estimates? Database, very good. So basically, what they are doing is these apps are analyzing historic traffic data. So the historical traffic patterns allow these maps to give you a very real-time estimate of what is the shortest route. That is what is happening. They are learning. They are learning very, very fast to give you a very realistic estimate of what route to take. Now, if you apply the same logic, and you know I told you drug discovery takes 10 to 15 years. Now, if you apply the same logic and say, okay, what failed, what worked, and you use all the historic data of failures and successes, now can you apply the same logic for drug discovery, where you learn from what has worked in the past, where you learn from what has failed in the past, what is toxic, what is efficacious, and actually identify potential drug candidates. You can do that, right? Now, let's understand how. Given that we understand that this is doable, it is possible, let's see how can we do it. All right, first things first, in a computer, any kind of math computation can happen only with numbers. Can you add A plus B? Can you add text? What can you add? What can you subtract? Division, multiplication. There are only 4 operators. Does any one of the operator works with characters? No. So machine can only read, and machine can read text, machine can read images. But when it comes to analyzing those, everything gets converted into a number, because only number can be mathematically manipulated. You cannot manipulate anything else. You cannot actually work with anything else. So now the challenge is, I showed you chemical structures, right? First task is, how do you make a computer read those structures as numbers? Right? So let's see how we do that. So there is a concept of line notations. Line notation means you start representing structures as linear string of characters. You saw a structure, it was a 2-dimensional thing, right? Structures are not 2D mostly. Structures are mostly in 3-dimensional. You're sitting on a chair, right? I can also draw a chair on screen. It will look 2D. But is it 2D? It is not 2-dimensional, right? It is 3-dimensional. You can always convert or project a 3-dimensional object into a 2-dimensional space. You can do that, right? So imagine, how do we do that? So there is a simple concept of line notation called as SMILES, Simplified Molecular Input Line Entry System. I'll give you an example. You will understand what I'm talking about. Forget about a lot of terminology. Focus on the concept. Okay. So, but just remember one thing, that in SMILES, atoms are represented by their atomic symbols. You are all reading chemistry at some class, at some level in your class, right? Right? You all have chemistry as a subject? Very good. So you know what atomic symbols are. It is very simple. Say, for example, what is this? Acetic acid. How do you draw an acetic acid? Is the structure correct? Is the molecular formula correct? Very good. So what I'm saying is, computer cannot read this structure. It has to be converted into something it can read. So you convert this structure into a SMILE. How do you do that? Very simple. So how it is? So it is like C connected to CH3, C connected to double bond O, C connected to OH group. Now if you see here, I have not mentioned hydrogen here anywhere. Why? So what is the valency of carbon? Right, absolutely, tetravalent. That means 4. So if I know that there is a CC bond here, I automatically understand that this C needs 3 hydrogen to complete the valency. This C might not need any because it is already occupied. Right? So based on basic principles of chemistry, you understand that you can very happily avoid hydrogens in SMILES, because explicit hydrogen definition is not that critical. You can still be able to extract this from here. Okay? Look at another example, ethanol. What is the SMILE of ethanol? Even simpler. CCO. So imagine what you did. You have actually converted something from a 2-dimensional structure into a single-dimensional string. So far, so good? Any confusion? Right now it's simple, right? Okay. Since now you have understood this, you tell me what SMILE this. So basically, can you guess this SMILE belongs to which antibiotic? This is just to tell you that even very complex structures like this can be represented in a single line. So if I take this, if I take the SMILE, I can actually draw this structure. Right? And this is an antibiotic called colistin. It is a last line antibiotic. Last line matlab there are actually no other antibiotics after this that can really work. Okay. So now we got the idea that from a 2D structure, we converted into a one-dimensional string, but it is still a string. It is still not a number. How will machine read it? The problem still remains. So now from this string, we convert it into a number. Let's see how to do that. So say for example, we have taken two compounds here. Compound 1, compound 2. Okay. Now as you can see, compound 1 has a functional group shown in red. Compound 2 has this functional group, but it also has a benzene ring. Very good. Now what researchers have done over years is they have tried to understand what is the smallest chemical entity one can represent as an index. When I say that, say for example, if I want to understand what is your basically how many people in the world are with your name, what do I need? I need a database with all possible names in the world, right? And then say, okay, this person appears so many times in India, so many times in US. But I have a reference, right? So what people started creating is something which is called as a fingerprint reference. And the example I'm showing you here is from PubChem. So don't worry about that. Just remember that there is every chemical entity can be represented. And this is only an example. There are many ways to represent this. From 1 to 880 index. It will get clear if I show you this. So say for example, in compound 1, what is the functional group that you see here? This one, right? Now this functional group in this library appears at position 433. Somebody has already predefined all the possible functions and given each function a number. That if it is at first position, X function will come. At second position, Y function will come. At third position, Z function will come. So they have identified 1 to 880 different small functions, functional group actually, that can appear, and each functional group is given a number in that index. Clear? Which actually tells you that in compound 1 at 433 position is where you actually, it will say, okay, I have found that functional group. So this is where there is some data. Compound 2, you have the same function, right? So at 433, you still have that function, but you also have another one at 688, which is your benzene ring. Okay. So in this index, you actually can say compound 1 has the functional group at 433 position. Compound 2 has functional group at 433 and 688 position. So far, so good. So there is a reference. Against that reference, you have mapped your functional groups. Now, what you do is, because compound 1 does not have any other functional group, in your entire array, you make everything else 0 except 433. 433 has a value of 1. There is no other functional group. So everything from 1 to 880 becomes 0. In compound 2, how many zeros will be there? Here, how many ones will be there? 2. One at 433 and one at 688. Because you now know these two functional groups are present in your compound. So now imagine you went from a 2D structure to a single string to a number that you wanted. So now you are able to represent your chemical compounds as numbers. Now you can do machine learning. Okay. Let us look at an example. So now you know this is 1 and 1. And now you see here it has 433. There is only a single one. Good. All right. Now imagine you have done a test on some X bacteria. You took some 100 compounds from that 10 to the power 60 and you exposed 100 compounds to that bacteria. 30 show you activity, as in 30 compounds are able to kill the bacteria. Remaining 70 are unable to kill. And you now want to understand which functional groups were really contributing to the activity. That is what is the objective is. You want to know what is the activity, right? So what you do, you generate something like this. All your fingerprints, I'm showing only 1 to 10 here, but you know We looked at 880. So all of you have worked with Excel sheets? With Excel sheets you have worked, right? So now imagine opening an Excel sheet with all the column headings saying fingerprint 1 to fingerprint 880. Your initial top 30 green ones which you found active and the below 70 ones which you found inactive. And the way we did 0 and 1 on the previous slide, which finger is present, you say 1. If it is not present, say 0. So now you are representing your data in a matrix of zeros and 1. And now you are asking a machine learning algorithm, can you learn from this data and tell me which fingerprint is important for my killing activity? What kills a bacteria? Can you tell me which fingerprint allows me to do that? Because identify that, you probably will understand how bacteria is being killed, and that can be converted into a potential drug. Okay. And normally these matrices are not in hundreds, these are in billions and millions and billions of data points. All right. Now there are many types of ML algorithms, and I don't really want to bore you with that because it is like a 6 months course that you normally get taught. But I'll try and simplify it for you in just one slide. Dr. Somdatta will actually inform you about a quiz which is after, there is a quiz that you can take on the JIGYASA platform. People who do that quiz well will get to understand and learn with us more on machine learning. So that's an incentive. Half of it you know now, how generate files, how do you analyze it. The rest half is when you solve that quiz and we shortlist people to learn further. Okay. So there are many machine learning methods. Some are supervised, some are unsupervised. So when I say supervised, unsupervised, I'm only saying that in here, I'm telling you FP1, FP2, FP3. I'm giving a column a heading. In unsupervised, I'll not do that. I'll just give the data saying I don't know what is what, you find out. In this, at least I'm telling the machine, these are actives, these are inactives. Okay. All right. So just a very simple intro. Supervised machine learning is a technique that actually will allow you to either predict a value using a regression model or can help you classify your data into 2 categories. Example we are looking at. Now the question for you, the example we are looking at, is it a regression problem or it is a classification problem? What are you trying to do? You are trying to segregate compounds into active and inactive. So is it a regression problem? It is a classification problem. It's a classification problem. Very good. Who said that? Very good. Because now you know it's a classification issue. Because you're dealing with zeros and ones. You're not dealing with a continuous variable. You're dealing with discrete, right? When you have continuous data, you use linear regression. When you have zeros and one and binary data, you use a classification based method, right? So we apply this. And how we do that, we can discuss when some of you actually work with us more, and we actually will do this hands-on. So you understand how this really, the process operates. Now, imagine you have a model. The model says, I'm very good at looking at what you have given me. Now you give me any compound, I'll tell you whether it is active or inactive. Why would you believe that model? It is like you taking a class, like today, and saying, I have learned machine learning. How will I know you have learned? So how does school test you for your knowledge? You take test, right? You take test. So you here also, if you see here on the screen, there is a training data and then there is a test data. You don't believe what machine learning model is giving you. You test it. You actually now say, okay, I'm giving you something I know the right answer for. Can you now classify it? So first I will test with the data for which I already know it is active or inactive. Ask the model, okay, is it really active? And now you know if 90% of your time your model is giving you the right result. So what are the marks for your model? 90%. What is good? 90% marks is good or 99 is good? Exactly. So you know that your model accuracy should be as high, it should be good. As low, it is bad. And when do you fail? When do you fail in a class? With what marks? So imagine your machine learning model giving you a 50% accuracy, which means what? It is random. Model is actually not doing anything. 50% of the time it is doing, 50% of the time it is not doing, it is actually not learning anything. It is a random piece of data. So you need to move away from 50% to 100%. That is what you do in your classroom also, right? You try and increase your marks by learning better. So you believe your machine learning model when you have taken a test of that model and the test says 90% accurate. Then you use it. If anything less than that, you don't use it. How do you calculate accuracy? So there is a matrix that you compute, which is called as a confusion matrix, with which you can calculate accuracies. Let's understand how to assess an ML model based on a wolf story. Okay, how many of you have heard this story when somebody says, okay, this a kid actually starts shouting, there is a tiger, there is a wolf, but there is no tiger, no wolf. And then people stop believing you because you're doing a false call all the time, right? So let's take the example of that story and see how do you assess a model. All right. Wolf, like when a wolf came, assume it's a positive class. When there is no wolf, it's a negative class. Negative class means wolf. When somebody is shouting wolf, the wolf is actually there. When somebody is saying no wolf, the wolf is actually not there. Agreed? So far, so good? All right. Now, in this case, what is a true positive? So imagine there was actually a wolf and the shepherd said wolf. Shepherd becomes a hero because he saved everybody's life because it was a true call, right? What is a false positive? There is no wolf. The shepherd says wolf. What happened? The villagers will beat him up. Then why did you wake us up in the middle of the night when there was no wolf? Right? So it's not a good thing. It's a false positive. What is a false negative? The wolf actually came. The shepherd said no wolf and the wolf ate all the sheep. Problem? Right? The wolf actually was there. But you didn't understand that. Last one, true negative. No wolf, no threat, everybody is happy. Got it? Apply it to your active compound and inactive compound data. If your machine learning says on your data that you know, reported to be active, your machine learning model says it is active, then it is a true positive because your prediction and your original data is matching. Right? What is a false positive? When it is reported to be inactive, but your model is saying it's an active compound. Problem? But not so much. Because you are actually probably have something else in the kitty which is not there. But it is not a serious issue. Serious is this. The false negative is reported is active, but your machine learning model has failed to predict it. Now you are actually missing potential drug candidates because they are actually supposed to be drugs, but you are not finding them to be drugs. And the last one is true negative. No activity reported, no activity found. Good. Now these four terms, true positive, false negative, and true negative actually go in formulas of accuracy, specificity, sensitivity. Again, if you want to learn that, solve the quiz and we'll learn that. But the basic principle is the same. You need to test your model to believe it. Without testing, machine learning models can be pretty much garbage. Okay. So what we have done so far? So far, if you see on the slide, if we want to predict solubility of a compound, whether a compound will dissolve in water completely, we have understood what chemical features describe that. And whether you do an experiment or whether you predict it, you still are going to get a similar outcome, which means we have understood what defines solubility, right? If we have not understood which chemical features define solubility, we cannot predict it so well. Now, with increasing experimental data, the accuracy of predictions will also increase. Now, just to give you an idea, if a compound kills a bacteria, that is not sufficient, okay? Because it can be toxic. We actually understood what thalidomide did to pregnant women. Pregnant women were fine, but who suffered? Their kids. right? So a drug can still be efficacious. It will still work for the disease condition, but it can be toxic. So it is not just efficacy, but it is also specificity. It is also how it is, say for example, if you take a drug and it goes and settle down in your liver, in your brain, will it be a good thing? No. The drug should either get out of your body from your urine or from your fecal matter, but it should go out after some time. Anything that stays in your body is going to be a problem. So now when you discover a drug today, you need to optimize all these properties, and for all these one can apply machine learning approaches. The same way we did one. Now in this case you can say active, inactive. In toxicity you can say safe and toxic. So you can pretty much describe any property in numbers. Okay. Do we have data to show it works? Yes, this actually, if you see here, it's not even a month-old article. Generative AI has been used to identify new antibiotics for a very difficult to treat bacteria which is called as Acinetobacter baumannii. Okay. What is generative AI? So how many of you know what is ChatGPT? Raise your hand. Yep. A lot of people know what ChatGPT is. What is G in ChatGPT? Generative. So actually the same concept that goes in making your ChatGPT respond to your queries, that same concept is applied here to understand how to discover drugs. You know what I'm saying? So everything can be good or bad. Please don't do your homework using ChatGPT. It makes your teacher's life very, very difficult. So don't do that. Play with it. It is very important to understand technology today because, you cannot, as if you can stop technology, you will not be able to do that. So knowing the technology and using it in the right way is what one should aim for, right? When we actually discovered nuclear fission, it can be used to generate a lot of energy for the benefit of mankind. It can also be used to generate atomic bombs. Obviously, none of us wants that, right? So every technology will have its good and bad side. Be on the good side of things, right? And that is what responsible citizens do. So we should also use technology the way people are doing it so that we discover something that helps patients get rid of infections which are very difficult to treat. Okay? Likewise, it is not just infections. If you look at, again, a very recent paper, this came like last week. So if you see here, AI method actually accelerated drug discovery of Parkinson's disease, which is actually a very growing concern in the world, by 10 times. So they learned from previous data and identified new compounds. So actually this field is extremely promising. And because you will be doing your engineering or you will be getting into medical or some field in a year or two, try to see that you at least, irrespective of whether you take chemistry, physics, biology, commerce, any subject, learn one programming language and you will see the difference. Data in all fields is growing exponentially and people who understand domain and understand this are the ones making a difference. You would like to contribute, right? So learn that. Now, some of you who attended Dr. Lippy's talk a few days ago in Futuristic Fridays, she actually dealt with structures. And AlphaFold is something which is changing the landscape of drug discovery for one simple reason. We all understand that basic processes of life depend on what proteins do, right? We have been trying to understand what is the shape of these proteins is. The reason is the shape decides the function. So if you don't know how the protein looks like, you don't know what it is capable of doing. So the first challenge is, now the challenge here is reversed. There we were converting a two-dimensional structure into a one-dimensional series. Here you want to convert a one-dimensional amino acid sequence into a three-dimensional structure, right? AlphaFold actually do that. If you give it an amino acid sequence, it gives you a three-dimensional structure. Now imagine anything that we have not understood so far in a three-dimensional space, you can do that now. So I'll not go into details of this, but without referring to AlphaFold in a drug discovery talk will not be ideal because this actually is changing the way we understand protein biology so much so that pretty much everybody in the world is actually using this resource, and it's a remarkable discovery, to be honest. It is solving one of the most difficult problems in biology. All right. In last few minutes, I'll very quickly take you to what we do in our lab. So since you know my name, it is Anshu Bharadwaj. So I call my lab as AB Open Lab. And the reason is pretty simple. Anybody who wants to try anything new in science, you're welcome to come and play. Science has to be fun. It has to have impact. So you need to have an open mind and an open lab to do that. And that is why the lab says AB Open Lab. I don't really say we do genomics, we do drug discovery. We do everything that can make a difference and help you learn. All right. So what we do in our lab, I'll just give you one example. We also develop ML models. And one of the most important machine learning models we have developed is to treat biofilms. What are biofilms? That's the first question. So how many of you have a dental plaque at some point? One, very good. How many of you have sometimes realized that the soap is very sticky, some usage? You feel that, right? And how many times you will slip on a rock because it has some green substance on it? It becomes slippery, right? All these places, it's because a biofilm is growing there. Biofilm is nothing but a colony of microbes. They are very difficult to treat in a hospital setting because they can be anywhere. They can actually pretty much can be in all implantable devices, which are your catheters, whether it is venous or urinary. They can be in your joint prosthetics. You apply this, artificial knee and stuff like that. If they are stuck to that and implanted in your body, the biofilm will continue to keep on growing and your knee is going to really, it's a disaster. You can have biofilms in wound infection. You can have biofilms in your pacemakers. You can actually have lung infection. All these places, as of today, we don't know how to deal with. Because as of today, there is literally nothing to deal with biofilms. And more than 90% of hospital infections, this is what you see. So we thought, why is that a problem? Because biofilms, there are a lot of microbes are staying together. They're helping each other and they're extremely tolerant to antibiotics. Imagine somebody living in an open area versus somebody living in a gated colony. Why everybody wants to live in a gated colony? Because you get protection. They also gate themselves properly and now nothing can really go inside. So we thought, why not develop something that can penetrate this colony and kill them like a missile. You go in and you blast and everything comes out. So we actually then developed a machine learning model to actually design such peptides. And I'll not describe details to you today. It's a web server that you can literally play with online. There is no login, nothing, right? And if you see, we actually have managed to predict anti-biofilm nature of these small peptides with 95% accuracy, which means what now? Your machine learning model has good marks, right? Which means you can use it. So that is the level of accuracy one is looking at. Okay? But one has to remember, these are all early stage drug discovery projects. Still now, 90% of promising drug candidates fail when we test them in human. Why? Because either we are doing an experiment in a petri dish or in a mice or in a dog. Neither that petri dish nor mice nor a dog, none of them is a human being. So obviously their biology, our biology is different. Forget about other species. Are we all same? Yes or no? No, we are same. We are all Homo sapiens. But then we are all very different also. So what makes you believe our biology is going to be so same that what works on me will work on you as well? Which means this failure can only stop if we understand the basic biology, what makes us different, what makes still human. All of us are different, but see this fun thing. 2 eyes, 1 nose, 1 pair of lips, 2 hands. The basic body structure is not changing. But still you see a Chinese person, you say, okay, Chinese, Japanese, differentiate, right? Phenotype is still so strong, but they still have the same architecture, right? Which means some things are conserved, other things are changing. So if you understand what changes, we know how the drugs are going to impact us differently. And that is the era of precision medicine. And this is again an example which I'm pretty sure all of you have heard about. This is a story which says that there are 6 blind men trying to understand an elephant. Is anybody understanding this as an elephant? Nobody says it's an elephant, right? Some are saying it's a snake, it's a tree, it's a spear, it's a fan, it's a rope, but nobody says it's an elephant. Why? They're not able to comprehend the whole elephant there. The same problem is with data today. No matter how many ML algorithms we are applying, the data is just so much so that we all are like blind people so far. This is how one has to understand the problem. What the elephant looks like, we are still trying to understand how the elephant looks like, as in what we look like in very, very great details. And for that, you need your creative mindset, proper training, which will help you develop methods. And then you need machines, because I told you numbers, right? You need to do some computation somewhere. So you need a very good combination of your creativity, methods, and machines to solve any problem. But in the end, if you don't apply common sense, you will make a mistake. And I'll tell you how. I'm showing you two graphs here. And for the sake of clarity, I'll read out to them. The first graphs actually tell me that it is the number of people who drowned by falling into a pool correlates very strongly with whenever Nicolas Cage, who is a Hollywood star, appears in a movie. Does it make sense to you? You are saying when a Hollywood star acts in some movie, a lot of people die by drowning. What is the correlation? Nothing. So it's not actually fitting in your common sense, right? Sometimes data will show you these things. And that is where you have to apply your common sense to discard these observations because they are not true. Let me give you another example. The one graph on the right side. It says that it is actually a very strong correlation between US, United States of America, spending on science, space and technology versus suicides by hanging, strangulation and suffocation. And it's a very strong correlation. But do you believe this data? Is there a reason for you to believe that? Doesn't seem to be a correlation. Data will give you everything. It is your domain knowledge. It is your understanding of the subject. You should be able to segregate the actual observation from something which is only a mathematical observation. There has to be some evidence to say that this is true. Looks like a very spurious correlation, okay? So you can use AI, you can use computing, but you still have to use natural intelligence to solve problems. And if we do that as a team, that is where the solution is, right? If we all, but imagine you say we work on a supercomputer, our brains work faster than a supercomputer. So imagine all of the supercomputers sitting together and trying to solve something. You will solve it provided you know how to do teamwork, right? And if you're trained well, and you're with an open mind and you want to do teamwork, there is no problem in the world that is not solvable, right? This is a message for you guys. So I will take another 5 minutes and try and conclude with the fact that we can use AI and ML to do drug discovery. Still, it takes 10 to 15 years. We are yet to arrive at a stage where you have a disease today and you have a drug tomorrow. We have not reached there yet. Which means what? The drugs we have today should be used very, very cautiously. And why do we do that? And for that, I have taken an example of antimicrobial resistance. We all have lived through a pandemic. So I need not tell you what a pandemic is, right? Everybody in the world was sitting at home. That was the impact of the pandemic. How many of you have classes from home? Everyone, right? So we were stuck in our houses and everybody in the world, whether it was US or UK or India or Europe, every country was impacted, right? So when pandemics happen, this is what happens. No country has a control over it. AMR is also a silent pandemic because COVID, everybody knows. Do you know AMR is a silent pandemic? Or it is a pandemic? Nobody talks about it. So that's why we are here to talk about it. We know what a pandemic is, so I'll not describe that. But why are we saying AMR is a silent pandemic? Because antibiotics, which are basically these drugs to fight bacterial infections, right? When they stop working, as in the bacteria has figured out a way to not let this antibiotic work, is that when we go into a pre-antibiotic era. Which means what? Which means that when there were no antibiotics, and then you have antibiotics that don't work, is the same thing, right? And that is what is called as antimicrobial resistance. Just to get more clarity, if I have a group of bacteria here and I expose them to antibiotics, the ones in silver die. The golden one is the one which is resistant, survives, and that is what proliferates. So imagine what happens when you take antibiotics. You are killing the susceptible ones and promoting the ones that cannot be killed by antibiotics. Now, how do you kill them going forward is the problem, right? And then there are many mechanisms. This is for you to go back and read. This is something that we can discuss offline because there are just too many ways in which bacteria actually can do that. The challenge is, no matter how much AI ML we apply, no matter how much drug discovery we do, AMR is an evolutionary phenomenon. Bacteria are learning to evade the impact of such molecules for 3 billion years. So the natural learning process is of 3 billion years that we are trying to understand. And that is why it is important to use antibiotics judiciously. Sir Alexander Fleming, when he made the first discovery of penicillin, in his Nobel Prize speech, he very clearly said, be cautious, use antibiotics properly. And when did he say this? 1945. Did we listen? No. What is happening? Every day in the world, in the most advanced countries, people are dying because of totally drug-resistant infections. No antibiotics are working today. It is not future. It is happening right now. You will see a lot of people, even among your family members, who will say, okay, I'm having antibiotics. It doesn't seem to work. Or the treatment is going on for months together. Right? So this problem is actually there. So what we thought is that why not actually start by making kids of your age understand the problem better so that you can bring that societal change within your families, within your societies. Because you're anyways given a lot of homework and you actually read a lot, we thought why not do a better option? We developed a video game. So instead of reading more, you play. And while you play, you learn how bacteria develops different and like resistant to different antibiotics, right? So I'll not play the game to you, but I will only I'll only play a small 1-minute teaser, and then we can conclude it in another 2 or 3 minutes. The video is also available online, so you can check it. So it's not a single level game. It's a multi-level game. So with each level, you learn a concept on AMR. So I would recommend go and play. The overall message is antibiotic dose when prescribed, finish it. Don't over or underuse it, and don't use antibiotics given to somebody else. Okay. It also has other levels, but maybe I would leave that you to explore. We are endorsed by WHO. So the game is actually endorsed by WHO, and we were one of the top 5 games in the International World Game Competition. So it was done very, very systematically. We did playtest in several countries to understand how kids respond to the game, and seems to be a good response. And now it is part of the Jigyasa platform. So as Dr. Somdatta was telling you that you can go to the Jigyasa platform. There you will find the game and other things associated with the game itself. So I would recommend you to go and play. We in our lab do a lot of other scientific things, But the objective today was to teach you and get you excited about the basic aspect of things. 1 hour lecture is really not a good enough time to train you on any aspect of science. It takes time to learn. But this was an effort to make you understand what a drug discovery process looks like and where AI can help. And we looked at only one small aspect of AI where we looked at how one can mine a meaningful piece of information from a very big amount of data by converting structures into numbers and analyzing those numbers. Okay. All right. I've worked with a lot of students, but these two are very, very important because both of these kids came to my lab when they were finishing their 11th standard and 12th standard. So they're actually your age kids when they started doing science. Okay. Pooja actually went on to become a Gates Cambridge Fellow. She just finished her PhD from York University in UK. And one of my highly cited papers, the one that I showed you today, the machine learning model for anti-biofilm peptides, she is the first author of the paper. So she actually published the first machine learning model to predict anti-biofilm peptides in the world, being a school kid. The second one, Ashma, did a group chapter with us on basically drug repurposing approaches, right? She actually got Johns Hopkins University full scholarship to do her BS. And then now she is a joint PhD student between Caltech and NASA and doing PhD there. Just to convey to you, science does not need a degree. If you are passionate about learning, you can pretty much start at any age. And this is an example to show you that it really works. You don't need a degree. You need passion. If you are interested in truly solving problems, you can do that. And this is just to show you that in our institute, we actually develop a lot of such resources. And if you see at the bottom panel, we get a lot of hits from all over the world. So what we developed here is not very, it's actually pretty international in nature because a lot of international labs access our resources. I would like to thank a lot of people I work with because none of what we do in our lab is possible without a team. And I happen to have a very good team and very good support from both international and national agencies. This is my current 2 or 3 people are missing from here because they joined last week. I'll add that. And since the talk is also webcasted online, if there are people listening to the presentation, I'm looking for project scientists, project associates, PhD students, and you can look at our websites. And with that, I would like to thank you and would be very happy to take questions. Somrita, are there questions online?
No, I mean, there's one question, but I'm not able to really comprehend what the person wanted to ask there. I mean, I'll still read the question if it makes sense to you. They say, ma'am, how did we convert the compound into 880?
Oh, no. So basically, I understand the question.
Okay.
So what he's asking about is the fingerprint index. So the fingerprinting index is nothing but, just a second, Sumdita.
Yeah.
Yeah. So what people have realized over a period of time is we are trying to play with a lot of methods to start representing chemical structures to its last entity. So that can be converted into a number. So many people have started to generate a lot of fingerprint-based methods to see how chemical structures can be represented in the most finest possible manner. What I showed is one of the ways by which PubChem does this. There are other methods of fingerprinting which use like 160 fingerprints. Other people use even bigger, like more than 1,000. So there are multiple ways in which these chemical structures can be broken down into even smaller entities to say, do you have a double bond? Do you have a single bond? So everything can be represented in that fingerprint and given a number. So you know if that property is present in the compound, at that position you say, okay, present 1, not present, you keep adding a 0. So that is how it normally works. What I showed you was an example from PubChem.
In 880, 8 will stand for something, the second 8 will stand for something else?
No. So it is 1 to 880 ways in which it can be like
Got it.
entities in which can be 8. 80 is a number in itself.
Okay.
It's an index. It's 1 to 880. So how do I say? Say, for example, the first position represents that this compound has a single bond. The second position represents that this compound has a double bond. The third position says this compound has a triple bond. So if any compound has only single bonds, the first position will say 1, but the second and third position will say 0. So you know there are no double bonds in this molecule. Likewise, each of these property is placed at a particular position, one end to the other end. And wherever the property is present in the compound, you say 1. If it is not there, you say 0.
Okay. So the same person sent a follow-up question as well, that how does someone calculate this index? So some of it you already covered, but what I'm probably thinking is that probably the person will also want to know, how does one know कि अच्छा यहाँ पे double bond है?
That is why you converted your structure into smiles. So smiles actually carry that information with them. Because I showed you 2 examples, one which does not have a double bond and the other one which has. So these programs are basically customized to read smile strings. And if there is no double bond there, it knows there is no double bond. There is no triple bond. So it will make a 0. And if it is present, it will say, okay, it is actually there. So that is one of the ways in which you represent. This is not the only way, but the catch is, since you have converted your 2-dimensional structure into a string, that string happens to capture that data, which gets translated into a fingerprint.
Right. Right. That's
Any
all the
questions
questions
here?
that we have on. Yeah.
I'm asking the audience here to see if they have any questions. No questions? So one of my teachers used to say, if there is a class and there are no questions, there can be only 2 things. First, you have understood everything. Second, you have understood nothing. So I'm hoping it's the first one, which is very unbelievable. So if you have understood something, ask questions. Never ever in life refrain from asking questions. It's very important. It's important to be curious. Yes.
Anshu, can you please ask them to speak on the mic? Then the online
Right.
audience
So
will also be able to hear.
I will repeat the
Or you
question.
repeat the question. Yeah.
Yeah. So one of teachers is asking a question that antibiotics are so easily available in the market. So how will you literally, monitor their use? And I am happy that you asked this question, and that is exactly the reason why the problem is government comes up with a lot of policies, but they are very hard to implement given the how India is. We have a very broad spectrum of economic, the way we are stratified. Yes, exactly. Because this is again a myth. Not every doctor is trained in infectious diseases. And that is where stewardship, where you train doctors to make sure that this does not happen, is also important. We assume a doctor is trained in everything. It doesn't work like that. The doctors are trained in different specialities. Infectious disease is also a specialty. They know what to do. And that is why what we are also intending to do is every stakeholder, like a pharmacist, or say, for example, school children or their families, all of us, if we stop doing what we do, as in just stop taking antibiotic after 3 days, or the doctor gave me this, you also take this, might work with you. How do you bring in a behavior change? The biggest problem is going to be changing the behavior of people. Because even if you have so many policies, the implementation is as successful as people ready to accept them. I'll give you an example. When COVID happened and you were advised to wear a mask, why everybody wore a mask? You did wear a mask, right? I'm pretty sure all of us sitting in this room and online wore a mask. Why? We were afraid of catching infection because we knew there were no drugs. We knew there were no vaccines. So if we knew that there were no vaccines, no drugs, this could kill us. Situation is no different here. We just don't know. It's the same scenario. COVID is not the only infection. And that is why making sure that these concepts reach to a wider audience these kind of platforms are very much needed for us to make sure our kids understand what world are they going to get in their lifetimes. So that is where the issue is. We need to make ourselves aware. If we don't change behavior, no matter how much drug discovery we do, we'll keep falling behind.
But if it is not available in Mumbai, we will not data availability पे है ना, हमें easily available.
You are right, but now you imagine remote places where there are no doctors, people are sick. What do you expect?
What about medical prescription we are getting from the chemist shops easily?
This is a problem. You understand? So Somnata, I think this is a problem that we have to deal with superheroes and superbugs, as a team. So the audience is saying that why are antibiotics freely available over the counter? So if there is a policy intervention which says without prescription you cannot get one, then the problem automatically gets solved.
ऐसी बात है, नहीं देते।
Right.
जो तो बोले बात लगाए।
No, that is true. Those are essential medicines, है ना?
I'm sure we can't hear you. You're on mute.
Actually, so Sundata, the question is that if there is a very strong intervention by government saying these medicines will not be available without prescription, then the problem should get practically solved.
Mm.
So that is what I'm trying to make them understand. Yes.
I'm sure Joshi Joseph also wanted to ask a question at some point.
Yeah.
I don't know if he's still around.
Samdita,
Hello,
can
ma'am.
you hear me?
Yes.
I just want to
Hello?
ask कि एंटीबायोटिक रेजिस्टेंस ट्रांसफर हो सकती है फैमिली मेंबर्स को या एनवायरनमेंट में क्या कि एक इन्फेक्शियस या कंटेजियस मतलब कि क्या ऐसा भी कुछ हो सकता है जस्ट आई वांट टू आस्क दिस थैंक यू
Yeah, so the question is, does antimicrobial resistance spread among family members? So see, antimicrobial resistance is because an infectious bacteria was already there, which now is not also treatable. So the original property of an infection is to spread. The spread continues. And what now spreads is the version which is not treatable. And that is what makes the problem even more intense, because what is circulating now is a non-treatable version of the same pathogen that could be treated 10 years ago. Now you have a version that is not treatable but transmitting. So that now you know where the problem intensifies. And this is a global issue. Practically every country in the world reports GR infections today. Everybody. Yeah, so Dr. Joshi is there.
Yeah.
Can you hear me?
Yes.
Yes.
Yeah, Anshu, it was wonderful talk. I really enjoyed it. I just want one clarification. Especially when it comes to antimicrobial resistance, is it purely a consequence of mutation, or does the bacteria has any intelligence? Like, what is your take on it? Is it the bacteria trying to evade, or it's just a consequence of mutations in bacteria?
Yeah, so the question that you're asking is very relevant because people have observed that resistance, genetic resistance, is just one of the mechanisms of resistance. There is also phenotypic resistance, which we are still trying to understand. So it's not that we understand completely, but genetic resistance only partly explains the resistance phenotype. There is also a concept of phenotypic resistance, which we today understand as a random behavior or stochasticity to say. We don't really understand it completely, but there are observations. And in order to say intelligence, I think that's a debate, because how do we define intelligence is the first question. But I definitely see that any organism which is capable of adaptation. So why bacteria are successful? Because they're adapting to anything that they're exposed to. So adaptation, their adaptive capacity is what making them so successful. They adapt and they change. They know how to do that. Imagine a human being who is very rigid. He or she will not fit in any environment. Somebody who is very flexible will go and make friends everywhere and will fit everywhere. The adaptation of that person will be more. So probably their adaptability is what defining the resistance so much, not just the genetic mutation. You are right on that.
Thank you.
All right. So if there are no further questions, let me thank you, Anshu. And that was a fantastic talk, and clearly getting questions from our colleagues as well as audience online and of course the audience sitting with you at IMTech shows how engaging the talk was for all of them. Thank you very much for making time for this session. And just a reminder for all our audience that this series, the online sessions of hearing from the experts will end here with this session. However, students have tasks to do more. You are supposed to go and participate in the 4 quizzes now, and the 4th quiz is going to be based on Anshu's talk today. And participate in all 4 of them. Your performance in those quizzes will decide if you are going to be selected for the online sessions where you are going to do hands-on activities. One of the sessions will happen in May for a set of 10 to 12 students, and for another set of 10 to 12 students, that session will happen in June. So do participate. You will also get an email on this only if you have registered for this session. So do that, ensure that you have done that. And everybody else otherwise who's participating in the quiz will, of course, get a certificate of participation. With that, I'll also close the session for today. Thank you all very much for joining.